Okay, so the next one is exercise 7. In this one, a is an integer which is not divisible by 7. Then we have to prove that 7 divides either a cube plus 1 or a cube minus 1. Actually, this is very easy. It follows almost immediately from Fermat's theorem. Since 7 does not divide a, so GCD of a and 7 is 1, and that's because 7 is a prime. So by Fermat's theorem, the sixth power of a is congruent to 1 modulo 7. That is, 7 divides a to the power 6 minus 1, which is a cube plus 1 times a cube minus 1. But 7 is a prime. So 7 divides a cube plus 1 or 7 divides a cube minus 1. That's just it. Let's see the next one. The next one starts somewhat strangely. It mentions that the 3 most recent appearances of Halley's comet were in these years 1835, 1910 and 1986, and the next occurrence will be in 2061. So we are yet to see that. Prove that 1835 to the power 1910 plus 1986 to the power 2061 is divisible by 7, is congruent to 0 not 7. Actually, these numbers most likely do not have anything to do with these years, anything. I mean, it just simply is a, I think so, that it's just a coincidence and a curious one that these just give us this fact. Okay. So we actually have to simply prove this congruence. We will start by considering congruences modulo 7 that involve only these bases. One can verify that the first base here is congruent to 1 modulo 7. One can verify means I want you to verify. What do you have to do? You just subtract 1 from this and show that it's divisible by 7. I mean, the difference is divisible by 7. And the other base here, 1986, is congruent to 5 modulo 7. To show this one, you just have to show that 7 divides 1986 minus 5, that is 1981. Hence, the first one is so easy because you have 1 here, and that's why 1835 to the power 1910 is congruent to 1. mod 7. And but for the second one, I mean for this power, we have to do some calculations. 1986 to the power 2061 due to this congruence will be congruent to 5 to the power 2061. Now we need to see what this will be. So it turns out that, well, this 2061 is divisible by 3, and it is in fact 3 times 687. Why did we isolate 3? That's because 5 cube, which is 125, is congruent to 6 modulo 7. So this power of 5 cube is congruent to this power of 6 modulo 7. And here again, you need to verify that 5 cube is congruent to 6 modulo 7. Okay, then what do we do about this? This is rather easy now, because you can replace 6 by minus 1. 6 is congruent to minus 1 mod 7, so we can use that fact. 87. Since 687 is odd, this power is minus 1. Now you just have to add this congruence and this congruence. This power 1835 to the power 1910 is congruent to 1 modulo 7, and 1986 to the power 2061 is congruent to minus 1 mod 7. So if you add the congruences, the sum of these two powers will be congruent to 1 minus 1, that is 0 mod 7. Adding the above congruences, we get what we want, that is okay, so that's the solution. Let's see another one. It has two parts. Part A is this. Let P be a prime and A is an integer that is relatively prime to P. Use Fermat's theorem to verify that this x, which is it's given as a congruence, x is a to the power p minus 2 times b mod p is a solution of the linear congruence Ax congruent to B modulo P. Before seeing part B, let us first solve this one. So what we are given, we have a prime number P and an integer A that is relatively prime to P. We then have to prove that this is a solution of this linear congruence. So what do we have to do? We just have to calculate Ax when x is this and see if that is congruent to B modulo P. That's it. That will do. We have, I am not going to write that we have this congruence due to Fermat's theorem. It will be very clear exactly where we are applying Fermat's theorem. So I want you to just see the calculation, and when you write a note or something from this video, you may be writing some kind of note where you will note down these solutions. There you will write everything. That since GCD of A and P is 1, so by Fermat's theorem, A to the power P minus 1 is congruent to 1 modulo P. So those things you write there. I am straight away going to do the calculation. A times this is congruent to this, but by Fermat's theorem this is congruent to 1 modulo P, so this is congruent to B mod P. Okay, so indeed this really is the solution of this linear congruence. Now we are going to use this solution to solve some linear congruences. Do you, however, remember how we solved this linear congruence when we were studying GCTs? In order to solve this, we actually had to calculate a GCD using the Euclidean algorithm, and then we expressed the GCD as a linear combination of the numbers whose GCD it is, and then that gave us a solution of this linear congruence. In fact, that way we found all the solutions, but that is something else. This is another way of finding a solution at least. It involves a high power of A depending on how large P is, but still you instantly have a solution. So let us now apply this fact to answer part B by applying part A. Solve the congruences. Three congruences are given. The first one is 2x congruent to 1 modulo 31. The second one is 6x congruent to 5 modulo 11. And the third one is 3x congruent to 17. What is the modulus? 29 here. So here also in the solution, I won't really write much. I will simply just write what this thing is. So what is the original congruence? Ax congruent to B. for this one our A is 2 and B is 1. So the required solution will be for the first one 2 to the power modulus minus 2, that means 29 times 1. Now we have to calculate 2 to the power 29 mod 31. So you can see that we can write 2 to the power 29 like this, because 5 times 5 is 25, 25 plus 4 is 29. Why have we specifically considered 2 to the power 5? Because that is 32 and 32 is congruent to 1 modulo 31, that is why. It will simplify the entire thing. 2 to the power 4 is 16, so this is 16 mod 31. Okay, so it is 16, and you can clearly see that if you substitute 16 for x, you get 32 here, and 32 indeed is congruent to 1 modulo 31. What will the next one be? Here A is 6 and B is 5, and the modulus is 11. You subtract 2 from 11, you get 9. That means here we will have 6 to the power 9 times 5, and the modulus is 11. So what can we do in this situation? In this situation, what we can do is we write the thing like this, and it's a fact that 6 cube is congruent to 7 mod 11. This is something you have to verify. Okay, so we are going to replace 6 cube with 7, and then again 7 cube is congruent to 2 modulo 11. Again you have to verify this. So these little verifications I am leaving to you. 10 mod 11. Yeah, you can see, you can substitute 10 here. So what will that give you? 60. 60 minus 5 is 55, and 55 is divisible by 11. And finally, our A in the third one is 3 and B is 17, and the modulus is 29. That means 28, 27. So 3 to the power 27 for this third one times 17. This one will be a little, I won't say big, but it will involve some calculations. For example, you can write this 27th power of 3, of course, as 3 cube to the power 9. 3 cube is 27. So you have 27 to the power 9 times 17. And what is this? This is 29. So 27 is congruent to minus 2 modulo 29, because 27 plus 2 is 29. Now you can see that although we have a minus sign here, but still we have reduced the size. Numerically 27 is larger than 2. So that's why a little simplification. Now 2 to the power 9 is minus 512 times 17, and minus 512 because we have a minus sign here. It turns out that 512 is congruent to 19 mod 29. Again, this is something you have to verify. So minus 512 will be congruent to minus 19. So that times 70 modulo 29. And in place of minus 19, we are lucky, we can write 10, because minus 19 and 10 are congruent to each other modulo 29. That's because 19 plus 10 is just 29. So this is 170. And finally, again another verification you need. This is congruent to 25 modulo 29. Okay. So this is a solution to this linear congruence. So let me just end this video here itself. You may have noticed the post that I made. That post is necessary. I feel that although we are solving all the problems so far, I mean almost all the problems, and that is maybe it's helping you, but the videos have become extremely boring and we are not really getting to anything. We are just going on solving problems and problems. You do understand one more thing, that I cannot really make a 2 or 3 hour long video where we solve say 20 or 10 or 20 problems if they are small enough. That's nearly impossible. I mean, I can do, but no one would watch it. So that's why per video I can show you at most 5 problems. That is why I have decided to leave half the problems to you. And let's see what happens by the end of this month. You go and check the post, you will understand if you haven't seen that already. But let's just end the video here itself, and tomorrow we again have, what did we do? Last week I actually entirely forgot whether we did topology or differential equations. We will see what we have tomorrow. I think it is topology, but we will see. Okay. So that's just it. So see you tomorrow. Until then, this is me, Lucifer, from a mathematical group. Have a nice night.